wondering if we're going through it too fast for what you want, or if you're getting enough in terms of knowing what the contents of the manual are and being able to look things up as you go along.
Speed is fine.
Okay. So you got to ask questions if there's a particular area you want to know more about. And if I don't know the answer, I'll tell you and we'll go on. So we got to finish up process management and then get into file management and I/O, direct I/O, cache I/O, be able to try to simulate some loads on Do or something like that and take a look at things. And then there are just a bunch of miscellaneous pieces that we'll be finishing up Friday. Interprocess communication, security, data migration, which is pretty much the same as on Unicos. Accounting, which is the same on Unicos, except it's vanilla Unix, not the Cray accounting package. And then the network type stuff. And being Cray people, we never dealt with network type stuff, right? NIS lookups and all that sort of stuff. Cray was always on its own off on the network plane. But nowadays they're clustering them together and NFS and all that sort of stuff, and those creates all kinds of complications. You know, one of the problems right now that the DreamWorks, Disney type customers have is that they're doing all kinds of mixed I/O into a RAID 5 type cabinet that they're running as their home file system, and they're doing all their production I/O through that single file system. And this creates a problem with all the diverse I/Os, large sequential movie streams that have come up, and people writing Hello Mom and stuff like that. And they need to be able to do production I/O in a file system that's directly attached to the CPUs that are actually doing the I/O requests rather than pushing it across the networks. And the only reason a lot of these sites have gone to NFS for all this stuff is the ability to back up and manage the file systems more easily, not for a performance reason. Administratively, it's easier to back up all these NFS servers than it is to go off to everybody's workstation and back up home directories and stuff like that there. So it's easier to manage a large file system that way. But NIS, being able to look up accounts and passwords, things like that. DNS, being able to figure out what the IP address is for a given machine. And in 6.5, SGI created UNS, which is supposedly a performance improvement on top of DNS, so that your normal DNS services would make library calls, but UNS would be able to understand the various different calls and make whatever sorts of system services they need, caching things, and be able to have some performance improvements. And then NFS itself, just being able to remotely mount systems, they're being used quite a bit in clusters. And one of my concerns in the future is this make part command. When we start taking a 128 CPU origin and partition it off into 432s or something, the NFS traffic is going to be going over that block transfer engine. And again, that block transfer engine is needed for file system buffer cache and kernel breathing. The kernel uses nodes round robin for everything that it does. And if those block transfer engines are tying up a node doing something, then you start getting performance delays. Yeah.
What have you heard about the current status of partitioning? Because we've been told to yank it out of our training materials. It's essentially really not supported in net marketing.
Well, customers are, it's there. I mean, customers already know about it.
But
I have the same problem with page migration, and actually I've got a customer, I've got to go to Chicago in December and teach a customer class, and there's a chapter in page migration and none of it works, and I can't demonstrate tools or metrics or anything. But our customers are expecting this sort of stuff, so I don't know where, I have no advice in that area.
you haven't heard whether or not they are intending to support partition.
I know it's not tested and everything, and we'd like to, keep people away from it and discourage it, but there are customers that expect to use it. Okay. I know of nobody in our data center that's using it either right now. So I'd like to, but they've got their hands full with all the other things. So I've got the same problem with page migration in general. Anyway, we're on schedule as far as I'm concerned. Were there any questions on what we covered yesterday? We're in the middle of process management, and I was on page 550, 551.
So Dave?
Yeah, go ahead.
Are you saying that page migration on which Irix is based doesn't work?
Irix isn't based on it. It's an added feature for NUMA machines. So your workstations and stuff don't use page migration. They're a paging machine. They have page stealing and swap activity behaviors and stuff.
Okay.
But this is page movement from remote memories to local memories to reduce memory latency.
Okay. And that doesn't possibly, it's not tested, is it?
Right. And not only is it not tested, it's not working.
Oh,
And the replication feature, if customers turn that on and it's buried in man pages, if customers turn it on, it'll panic their system. And that happened, and Mountain View came back to me and said, well, don't teach them about page replication. But you do a man replication and it's on the system. So you're stuck in the middle.
Is replication and migration, we're talking about two different things here. Neither one works.
Both are, that's correct. Migration is for read-write pages, replication is for read-only pages. Both are designed to bring the page to my local memory rather than going across the router circuits to be able to get to my data. So it's designed to reduce latency. But again, in a cache-based machine, as long as you don't bust cache, you don't need to see those effects. And it doesn't matter that it's going across the router, except if the routers get busy. How many people have seen OView? Let's see if I can bring it up here. OView is a three-dimensional tool. You will not be able to pop it up in normal X environment. You need to have OpenGL and normal SGI environment available. But if I were on Flurry, I probably should log into Flurry and see what I can do there, maybe pound on Flurry today instead of do. But this is showing the topology of my system and the router activities that are going on. There are hardware statistics to tell me how busy those links are. Now this was originally part of Performance Copilot, but in 6.5 it's bundled. And I can see all my CPUs. There's 2 CPUs per node. So I've got 2, 4, 6, 8, 10, 12, 16 CPUs on the system. Okay, 4 routers. Now in the middle here is migration interrupts, this little brownish thing. And if I had page migration interrupts occurring, in other words, there are hardware counters on this hub chip that are on each board, keeping track of on-node and off-node references and whether they're read-write or read-only. Okay. And if I get so many off-node versus on-node, there's a migration threshold you can set that says if a percentage, the default is 90, if more than 90% of my references are off-node, then I generate an interrupt to the kernel, and the kernel decides what to do with that interrupt based upon memory pressure and traffic. If these are too busy, then it's not going to use them. In fact, we got an application that looks like it's 4 threads wide that's locked into here, but at the same time, I suspect that it's bigger in memory and busting the memory on these 2 nodes because there's router traffic going on elsewhere. And I'm on do, let me just go to my background here, *big R would tell me what I've got in terms of free space, and I can see that empty, I've got about 11,000 pages out of 131,000 pages. So I've got one application running 4 threads wide that's taking most of my memory, so it's busting memory on the node, and OView is showing the router traffic to get to the rest of its data. Now that may be to its advantage. There are 2 trade-offs here, latency versus bandwidth. If I keep pulling all my pages into my local memory, I'm restricted to the bandwidth of that local memory. Here's my rule of thumb in terms of page migration if it works. As a system tuner, stay out of it because not every application benefits from the same migration policy. Some will benefit, some won't. You're better off having the application people set their application up to have proper placement in the topology, into the architecture. dplace, for example. Now, my rule of thumb is if it's a small threaded, large memory application, you don't want page migration, you want bandwidth. And this application, Dyna 3D that's running right now, is big in memory, but it's only using a portion of my CPUs. So I could either go wider and bust my program down bigger or into smaller pieces that then fit into each node, and then each thread only has to reference data that fits in its node. But they haven't gone that wide, so now they're busting their memories and having to go across the topology to get to their memory references. And that's why the routers are showing heat, even though we've only got 4 threads on 2 nodes, because it's not fitting into the memory size of those 2 nodes. But single-threaded applications, they're big in memory, have a big data set. So if I had a 16 gigabyte process, single-threaded, I'm going to want bandwidth and distribute my data round robin among all the nodes. And that's what we've always done in Craze at a word interleaving type of thing, except this is page interleaving. Okay. However, if I'm multi-threading, then I want latency. I want to be able to break the data down into pieces that fit into each memory, and then the data that I work with should be in my local memory, assuming that I've properly programmed and fit this thing into my architecture. And then I want latency and page migration if I do happen to get pages pushed into some other node or something like that. Or if I thread hop, if I lose my affinity in the CPUs and jump to a different part of the architecture. And that could happen due to real-time daemons, including NFS daemons. If you had a whole bunch of NFS daemons running real-time, one per CPU, they can drive your work out and you start hopping around in the topology. And then your pages start following you around too, page migration bringing them in local. Okay. So normally, if page migration were working and on and stuff, in 6.4 there was absolutely no problem right now to be able to see migration interrupts occurring in this situation because it's referring pages off node. And then you can configure, if it worked, with Systune and a couple other tools, the pressure threshold, say how much memory needs to be available on that node. If there's not enough memory available, don't bring it in. If these routers are busy, don't tie them up with page migration traffic because they're busy reading in data, stuff like that. Okay. And if you logged into Flurry or something, this gets real interesting. It eventually gets, like on a 256 CPU system, it gets difficult to see. Oh, let's see. If Typhoon even comes up. Now, this is Performance Copilot. And it's using an open inventor interface. This is standard SGI interface, and you've got controls over here. But one of the things to know about with these tools is this arrow. If I place it over one of these things, the box up above is going to tell me the metric name. Unfortunately, I can't grab it and paste it into a window and look it up. Now, there are other tools where they do have a pop-up metric description type of thing. But let me get back to here. The key thing that you can do for the entire data metric pool within Irix is a command called PM-info for your performance metrics information. This is where all your metrics are defined. And this is part of Performance Copilot software. And if I do a capital T, and I'm not going to specify any metric name, which is going to give me every metric, and I'm just going to put it into a file called info. And now I can take a look at the metric pool that I have on my system. And Performance Copilot, Gross View, Top, all these different tools, this is the entire metric pool that they're getting into, and the description of these various metrics. And I'm also defining all these metrics within my web pages and the materials for the Origin tuning class that I run. Okay. So if I, for example, on this one, went to this brown area, it says it's Irix NUMA migration interrupt total. So these are the interrupts that the kernel's picking up due to the hardware recognizing off nodes being higher than on nodes. And then I could go off and let's see if it even works here. GR_SN is the graphic interface to configure this, and it does come up. And right now it is configured as on, and I've got various options. I can kick it to normally on. Let's just see what happens here. On is on all the time, and that's the way it was configured, yet there are no interrupts showing up. And if you look at all the metrics, there's no indication that page migration is working. Okay. Now, on is on all the time, off is off all the time, which is what it appears to be all the time right now. No indication of it ever being any other setting. Then normally on says it's normally on, but users can turn it off, or it's normally off and users can turn it on. Okay, and dplace is the way that you can turn it on or off. And then you've got this threshold, and this is right now set to 50, saying that if more than 50% of my references are off node, then generate a migration interrupt and decide what to do. And the rest of these are my filters. Dampening is saying don't worry about short transients bursts to a particular page. We want to look for long-term patterns. So the dampening says ignore a certain number of interrupts within a given interval. so I don't get a lot of noise. Then there's something called unpegging. These hardware counters do not reset themselves or wrap or anything. They go to a top and clip. So we have to unpeg them and set them back to 0, and this is done through software. This is another indication that page migration is not working, because when it's on, the unpegging routine will show up in your system time. And there's a tool called TopFunk. Now, for those people that actually do deal with software, there's a module called NoShip. sw.perf. And in there are two tools that are useful to you. TopFunk and TopWait. And TopFunk is a curses type tool that gives you the name of the routine that your system time is. So you constantly have a curses tool giving you top 10 kernel routines. Okay? And unpegging would normally be in there if we had that sort of activity. So there's no indication from any sort of metrics, including the kernel stack itself, that it's ever executing any sort of NUMA software. Now, it doesn't matter on our indies, but it does matter on some sites where they think that it's going to benefit them. And NUMA isn't as big an effect as cache misses themselves. And the biggest thing I teach in my classes is that you just want things to lock down in the CPU and be completely undisturbed and not bust cache, and you don't see any of these NUMA effects. And there's also prefetch operations that hide it. It's when you actually get more jobs than you have CPUs that you get into the problem. And the key tool, let me get out of this, but it indicates that migration is on, yet there's no other indication. So anyways, that's let's see if TopFunk is on the system. No. One of the problems you're going to find, by the way, in 6.5 is the overlay layered software. And there's a couple of modules that you'll have conflict problems with. If you ever tried to load EOE SW Audit is the other common module. That's for the security Daemon software, security audit trails, and extended accounting data. Both of these things have got kernel changes in their mods, and you get into conflicts and have trouble loading them after the fact. So no indication of page migration working from do the way it's configured right now. And in Systune, a lot of the SN was simply a GUI interface to the Systune parameters. And in Systune, there's a whole bunch of parameters here to define the page migration activity. Don't mess with any of them. Okay. We got into this because of your discussion about pulling out make part. So this is the same kind of story. But in here is replication. NUMA replication control enabled. You turn that on, you're going to end up with a panic system and battle between the customer and software division. Nobody's testing this sort of stuff, unfortunately. But I'd like to get back on subject or finish any other questions. But this is a good example of something that page migration should actually be occurring. It would not benefit the application. The application would be benefited by the bandwidth that it can achieve by distributing its data across all the nodes. But if it were to thread wider and fit the data into its memories, then page migration would make sense. And sometimes the thread width should not be based upon the CPU work you got to split up, but the memory work you got to split up. Okay? So that you split it up in enough pieces that you're not busting the local node memory. And then if there's an occasional problem, then page migration makes sense. So I say stay out of it, let the application programmer set it. D places the command to do that. This is all unique to Irix on NUMA architectures, the Origin product line. No other company has anything like this page migration concept. And I've never seen anything like it within the T3E product.
Yeah, we don't have it.
Yeah. That's right.
Hey, well, you were saying in some cases it might be beneficial to spread it out across more processes. How often is the executable malleable when you have that?
That is an environment variable setting. In The man page is man PE_environed. I'm not sure if I'll have it on here. PE_environment is your programming environment, and it's something that you can set up at runtime. So you can switch between simple threads, dynamic threads. You can suggest a thread width. You can say it's definitely stay to a thread width. Okay, but
Well, what I was saying is, doesn't it even somewhat application specific? I mean, certain applications are not going to be that valuable.
there will be scaling problems within the application. That's correct. And certain applications are not multi-threaded yet. I'm just starting to see parallel versions of Gaussian and Nastran, which have been traditionally single-threaded. So yeah, you've got all kinds of trade-offs. The biggest thing in system tuning is to understand the workload first and see if you can fix the workload if there's a problem there first. I always try to solve it at the application side first. The other thing about system tuning is you're sizing. You're basically sizing things to give it the resources that it needs in a friendly chunk size that's usually related to some alignment number, whether it's cache line alignment, page alignment, sector alignment, track alignment, some sort of geometry question that you're trying to match. And we're going to talk a little bit about that when we get into I/O. So by going wider threads, I'd be able to break the data sets into smaller pieces. At some point, I would hope that I'd be able to break it up properly such that it fits into my local memory so that I'm not busting it. But then the scalability question of the more threads you have, the longer it takes for them to all communicate to each other. The more people on a party line, the harder it is to understand what's being said. Kind of problem. So some applications don't scale. And one of the codes I use in my tuning class is a 30-year-old code that was even run on Cybers as a diagnostic to check functional units. Does not scale because it's such old written applications. The algorithms in it don't appropriately apply to this situation. And you got to get people to rewrite the stuff. I mean, things that were written for Cybers and Craze have to be rewritten for an origin architecture. And nobody may want to do it because it was written by somebody that retired 20 years ago or 30 years ago or something like that. So there are two trade-offs in page migration if it were to work. One was the latency side of it when I break it into small problems and I'm constantly fitting my data in local memory. And the other one is the bandwidth advantage, being able to take advantage of the nodes and think of them as a bank interleaving concept. Any other questions right now? We're in the middle of process life, and I want to look at 550. I skipped over a couple pages about background processes and pauses, but the main point here is that we've got three states, basic states that the process is going to be in. One is running, where it's actually connected to the CPU, executing, and with top and PS you'll see a CPU number. Runnable, waiting to run. It is not sleeping on any lock or anything like that. If there were CPU available, it would be able to connect to it. And the third one then was sleeping, or often referred to as blocked. Okay, and we can intentionally block by doing pauses and waits and sleeps. That's what a couple of the previous pages were. Or we may be put to sleep because of some other lock contention where we went into the kernel and the kernel says, my logic to handle this is busy right now because somebody else is asking me to create an inode, for example. So every time I create an inode, I set an inode lock, do my work, and then get out. Now, for example, on a news server, there are a lot of inodes where I'm always busy manipulating inodes for all my different news articles. Okay, so that would be an example of a lock, an inode lock. So on page 550, they're just talking about some of the different sleeps that I could occur on. Physical I/O completion, I go to sleep waiting for my I/O to complete, and I/O done. There's actually two locks for the I/O. There's a lock called buff, and there's a lock called BIO. This is your NBuff, and this is your direct I/O, bypassing file system buffer cache. And one of the things I want to show you here, in 6.5, let me pick a larger window here. I can go into var sysgen system, and there's an irix.sm file in there. This is a configuration file for the kernel. Now I'm not going to do it on this machine because I don't have root here. But in there is a K-sync for kernel synchronization objects to be able to get the lock names. Instead of with the wait chan address showing an actual software address, I can see the name of the lock that the thing is sitting there sleeping, waiting on. And a little bit down here then is the include. If I change that from K-sync to K-sync underscore name D, if I change it to that, PS will then show me the name of the lock that I'm spinning on instead of the address. Like I said yesterday, Irix is better instrumented than Unicos and Unicos MK. There's a ton more metrics and capabilities and tools. And let me bring my font up. Just in file system buffer cache, there's 100 different metrics and tools more than Unicos has. So now if I do a PS-EL, as we were doing yesterday, I can now see the names of the locks that I'm waiting on. A dash says that in this case it's defunct and terminated, but it could also be running. Okay. So for example, here's LS Dyna that was running. So I got PIDs and all those sorts of things, but there's no lock. It's tied to a CPU. In fact, the CPU it's in is CPU 1. And there's also thread in 2 and 3 and 0. 0, 1, 2, and 3. Those were the CPUs that LS Dyna was tied into. Not sitting on any lock, but they do have terminal. It is tied to a terminal. It's not a batch request or anything like that. It's actively tied to a terminal. Now, if you ever get into these locks, I am listing them off on my web pages. And it's in the CPU utilization tuning chapter that I have. And I'm in the process, I've grabbed all the lock names, but I'm in the process of trying to get the description of the locks, the kernel routine that manages that lock, and then the type of lock, whether it's semaphore, mutex locks, things like that. Different software methods of locking, setting locks. And for example, BIO lock, here's the XFS INO for the inode lock. We're going to talk about XFS logs. BIO is the physical IO to disk. Looks like a pipe lock. You know, a variety of different lock names. And I don't know all the lock names, so I'm in the process of trying to basically go through all the source code and document them piece by piece with help from Kerm and some of the other people in my group. So 5-50 is just talking about this, and what I was trying to say is if you want to understand what this lock is, that's the way you can do it. This ksync underscore name D will turn on the name of the lock, and then you have to figure out what that lock means, either through the source code or looking it up in a table such as I'm trying to build. Okay? So on 550, they're talking about physical I/O completion. That would be things like the BIO lock for direct I/O or buff lock. And by the way, it's a null, zero null field, so you may see zeros at the end of it to fill out the whole field name or something. So there may be zero stuck on the end of that lock name because of the way it prints it out. There's a lock for waiting for paging, for memory paging when a process accesses a memory page that's not allocated physical. Both buff and BIO locks are used for paging. Paging is an I/O operation, and VHAND uses the threads that normal file I/O uses. So paging activity and file I/O activity are done through the same mechanism and counted in the same bucket. So you could have an application that's paging, waiting for a page to come in with a BIO lock set, and is waiting for it to come in from swap. Or it could have been an I/O request, such as a read or something like that that's happening. And again, the process will sleep on the BIO lock until the page is loaded into memory. There's also voluntary suspension for sleeps and pauses, things like that. Pipe empty, pipe full locks. Child termination of the wait lock. that sort of thing. We had kernel WT for kernel thread locks. Okay. So if something's just sitting there and it's not running, you want to know why it's sleeping, you can find out what that lock name is now in 6.5. So 551 is just talking about the life of a process then. We have the parent, typically the shell, and it's reading standard in. You type in ls or something like that. It's not listed here. You type in an ls, hit a carriage return, and then the shell is going to parse and make the appropriate system calls to fork and exec the ls. So in this example, the parent forks off ls and the process is created. PS will show it at that point, but it'll still have the parent name. Then it gets basically put on the run queue ready to run as soon as it was created. At some point it's going to be chosen to run based upon priorities or job class. I should say job class first. We go through the job classes. We look for real-time first, batch critical second, timeshare third, then opportunistic batch, then waitlist. Then we go idle if there's none of those. So the CPU scheduler is going to be using clock interrupts every 10 milliseconds to be able to check on this sort of stuff. And if a process has exceeded its time limit or exceeded its time slice, it'll get kicked out, particularly if somebody else is there waiting for it. So at some point it's getting chosen to run and goes to the third state where it is actually executing or running in the CPU connected. And it may be making system calls. So along the way, let's see, it's doing here, it's going off, running in kernel mode, but then forking off and running the actual application. And then the application may be making system calls or have floating point exceptions, page faults, or hardware interrupts. Things like that that are going to cause a software or hardware interrupt to force it back in the kernel. And you can actually turn off some of those interrupts and redirect interrupts, things like that. In the real-time market, you may actually turn off the clock interrupt on a given CPU so that it never gets interrupted. So you're running in user mode and along for some reason you make a system call, for example, and you go into the kernel and ask the kernel, please do a read for me. While in the process of doing the read, somebody else is busy doing a read. Only one person can change certain structures at a time. They have to single thread tables, and that's what the locks are for. So you go to sleep on that lock and you go into the sleep state and you wait for that lock to be completed. And the wait chan address is how I get back to the event that I'm waiting on. So eventually I get a signal, look up my wait chan address, and I know what event I'm going back to. Okay. And that wait chan address was extremely useful to have lock names so that you know what lock am I sleeping on. Eventually I wake up from the lock. Maybe it was asleep with the timer saying after 10 seconds, wake up again. So I get back on the run queue ready to run. I'm runnable. And then I get chosen to run again. Now the other path here, preempted, that was due to clock interrupts. I think we're going to see this in a couple more slides, but there's something called slice size. And that's basically the number of ticks you get before you lose your time slice. Rather than having 10 millisecond slices, on origins, for example, it's 10 times 10 milliseconds, or minor clock cycle. You get 10 minor clock ticks before the kernel says your time slice is up. And that's known as an involuntary context switch, because the kernel interrupted me because I exceeded my time slice. It's called slice size. That's a systune parameter. So on workstations, they have a short slice size. On compute servers, they have a large slice size to reduce secondary cache thrashes from noise of driving that thing out of the CPU every 10 milliseconds. Now it's 100 milliseconds. Whereas on your workstation, it may be 20 or 30 milliseconds, what you need for an interactive environment. So along I'm running, and the clock tick is the 10th one that I'm supposed to get. Kernel recognizes that, and I get preempted and put back on the run queue ready to run, waiting for that next opportunity when somebody else's slice size is exceeded or some other priority scheme interferes and says this person gets that particular CPU. Now the more you make system calls, the more chance you have of being put to sleep and therefore having to wait for a CPU. Now, in the extended accounting data, we actually track some of these statistics. So we know the service time, we know the elapsed time, but we also know the CPU wait time. How long was it on the run queue, ready to run, waiting for a CPU? We also time the two locks, the buff lock and the BIO lock. So in extended accounting data, there's a counter there that says how long did you wait on the buff lock? Or how long did you wait on the BIO lock? And eventually JA, if you've used that, reports those statistics. JA is a Unicode tool for job accounting to give you your timings. And I have a JA that I support on Irix right now that gives you, when you have extended accounting running, gives you the elapsed time, the service time, the system time, how long was I in the kernel, how long was I in user mode, and how long did I wait on BIO locks or buff locks, or how long did I wait on a CPU. It also counts out how much I/O I did, how many bytes, how many calls, how many times to disk, that sort of information. So with accounting turned on, and particularly with extended accounting turned on, I get timings of states 2 and 5. But not all locks are timed. Just the BIO lock and the buff lock. If I'm manipulating inodes, that's not in the IO locks, that's not in the IO timers. Process created with the fork allocates the necessary structures. Once the process becomes eligible, it's selected based upon classes. It eventually goes to run. It may eventually give up control. And the last thing then is it does an exit or a kill, and that's where it becomes a zombie. And in the zombie state, it basically has no user addressable space left anymore, but the system structures are still there. The process table entry, the user thread, user areas, things like that. And in the process, some of those statistics are being written from the zombie into file system buffer cache for accounting purposes, if accounting's turned on. And I mentioned before that if file system buffer cache is busy, the kernel may take a while to actually get a buffer to write that accounting record, and you may see defunct zombie processes around longer than you'd normally see them. And this would indicate that you've got a file system buffer cache contention problem. We're going to talk about that in the I/O area. So PS tells you the state that it's in, and with that ksync underscore named D, it'll give you the name of the lock the process is sitting on. Put fairly simply, this is just describing 3 different types of processes in Unix terms. The interactive process is what we're trying to do with VIs and LSs and PWDs. The batch process is the stuff that's CPU intensive, like that LS Dyna was CPU intensive. Where am I? On this system, I'm on do and Egan. Oops. The first health of the system metric is a standard SAR command. And I can see that this system is 25% busy doing user work. That's that LS Dyna that top would show me. Very little system time, so it's doing very little system calls at all. No interrupts going on, but key thing is there's no wait I/O. This thing is not I/O bound. Now this LS Dyna was pure CPU and pure memory. There appears to be no I/O load behind this LS Dyna. A SAR-C would tell me the number of system calls I'm making. I'm making very few calls. 200 calls per second is nothing. I can get onto systems in 500,000 calls per second. And it's only moving about 2 kbyte. So there's no I/O load behind this application. But the SAR-R was showing the memory pressure because my empty is down to 12,000 pages. And if I bring up GMEM usage, I'd be able to see the memory map. And it's not showing a whole lot here. Actually, it's showing quite a bit free here. Almost 1.3 meg. Not sure why. Let's see what else we have. Gross view. I'm avoiding RMMC right now because that was creating a problem. Yeah, I've got plenty of memory available on the system right now. Let me try something else here. Trying to find my missing memory. My missing memory is inactive data in file system buffer cache. See that big yellow piece? That's data that's been in file system buffer cache that I haven't used in 2 minutes, or actually 100 seconds by default. Okay. And in fact, this was the display that was going negative yesterday and going all green. I'm not at that threshold yet. That stuff should get released if I fire off memory work. My cache has grown real big. My cache is almost 80% of my memory right now. And most of that is inactive data, data that I've not used recently. Now I can find out what the names of those files are that are sitting in that cache with BuffView. And there's a couple of things here, dsplot, I'm not sure that those are them. We've got 100 meg, here's something sitting here, run RSF, it's almost 100 meg in size. But this is listing the names of all the files that are sitting in that full image. And I can, let's see, with a question mark, I can look at particular types of buffers, and I was interested in inactive buffers. That's what we were seeing before. So INACT should allow BuffView to look at just the inactive buffers, the ones that haven't been referenced in 2 minutes or 100 seconds. So F, INACT. Let's see what we get here. And in the process, it'll actually give the age of the data. I don't see any change here. It may be tied up busy. Let's see. Yeah, it looks like it's busy doing something. In fact, up at the top, one of the things we can see here is there's almost 90,000 buffers that are inactive right now. We're going to get into this a little bit later, but this is breaking out 125,000 total buffers to my file system buffer cache. This can allow it to grow to the entire memory size of my system. And it's 64 kbyte per buffer. Now, looks like it's just hanging there. I'm going to see if I can break out, do something else here. Here's BuffView. It's busy doing something. It's already spent a minute or quite a bit of time crunching whatever it is I tried to do with that inactive flag. It had 90,000 buffers it's got to sort through and figure out what it's doing probably. But it was actively running. It's on CPU 8. It's connected, all that sort of thing. So it's not sleeping on any lock. It's busy processing 90,000 buffers and figuring out what they're doing. See if it came back. No. And it's still busy doing it. Let's see. So what I'm going to try to do here, in the meantime, see what happens here. Pound on the system. And the kernel is releasing that space. I've asked for half a gig of memory basically, and it's going to push the kernel down, freeing up that free C, the inactive data. I haven't used it in recent history. I can reclaim that memory space. Let's see. Oops. I'll fire off a couple of them and drive up the memory load. Oops, we hit the bug. Just ran out of memory, but here now I can see what's going on without the bug, but now I can't see my inactive data, but now my kernel is definitely this size in cache, whereas before it was way up here. And in this display, it just showed up as green. It's the one with the bug that separates the inactive data out. And it's basically doing some arithmetic that has a subtraction in it, and if one's bigger than the other, then it wraps and goes super big. So all that inactive data was freed up. So I was just talking about different types of processes and batch processes. LS-DYNA was an example that I would basically was characterizing. It was CPU intensive, no I/O behind it, not a whole lot of memory behind it, which is what I was surprised about, because apparently the inactive data seemed to have interfered with the page placements, such that when we were looking at the router and showing that it looked like it was referencing data outside of its node, that the cache had grown so big on the node that it, for some reason, it allocated off of neighbor nodes. And I'm not sure why that happened. Keep in mind, behaviors change with every patch that you apply to your system. Other types of batch processes are submitted from a queuing system, and again, LSF is probably going to become the de facto batch queuing system. And the other reason for that is that we're giving NQE to them, and it's to their benefit to merge the products and have a single unified product to the user community. So I think NQS is basically a dead-end product now. And the main reason for that was NQS was designed with a queuing concept to it, meaning that the job has to sit in some queue somewhere. And if once you stuck it in the queue, it's committed to that machine and you can't move things around. It did not work in a cluster situation or an array situation where we could move things off to a machine that frees up or something like that. LSF works in a cluster a little bit better, treats the cluster more homogeneously. Then we got daemon processes. These things typically sleep. There's a lot of system daemons, system processes that are invoked at boot time. The check config sets up a lot of this stuff. It's not uncommon on compute servers to turn off most of that stuff. Okay, turning off media D if you don't need your CD-ROM all the time. All these daemons can chew away at your performance. Even on my workstation, the default is to have the web server up, and I don't need HTTP daemons running on my workstation. Everything's being served off of a different machine. And then it's going to an NFS file system to get the data, so why should I have CPU resources interfered with on my workstation for that HTTP daemon unless I'm actually using it and having people address my particular workstation address? But it's not. It's all centralized off to a common server. The daemon processes may not have any terminal tied to them. They may show a question mark, as we saw the other day within PS. And another thing I might point out about this, all that chatter, remember real-time daemons run before miser daemons, or real-time processes run before miser processes. And there's something that happens on origin systems or any cache-based machine, but down here we basically got number of workload units, number of jobs, number of processes, whatever you want to call it. This is a bottleneck curve I'm drawing. And over here is the time to do the work. Okay? As I have more and more people trying to get work out of the system, eventually something's got to wait. So you've got a bottleneck curve that looks something like this on cache-based machines. And this is the number of CPUs that you have on your system. Once I've got more processes than CPUs, I have to start time slicing, and I'm going to start missing on cache, and I'm going to spend more time reloading cache that I'd previously loaded, but I got kicked out. When I came back in, somebody else had dirtied my cache. And this is about a 7 to 10% increase in my service time because of the CPU scheduler interfering with me. So I always tell people, set your run limits and stuff like that less than the number of CPUs you have. Now the problem here with these daemon processes is that they chew into this and cause the bottleneck to occur earlier. And in one case I ran with all the daemons off, including NFS, including all the network daemons, everything I could turn off, and I ran the workload through the operator console. And the bottleneck was very sharp right out here. Then as I added NFS daemons, for example, there were 8 of them on the system. I could actually count out if it was a 16 CPU system and I had 8 of these daemons, I could count them off and figure out exactly where that bump was occurring, less than the number of CPUs I had on the system. Okay. So this is known as system cache thrash behaviors. Now when you install LSF, it'll automatically set your run limits to the number of CPUs you have. But it doesn't take into account the real-time daemons that are going to be noise, that are going to drive you out of your CPUs before you hit that CPU subscription ratio of 1. And I'd seen this manual here, the System Support Handbook. Mentions some guidelines in here about tuning. Actually, it was the, I guess it wasn't the tuning page. Yeah, here we are. And SAR-Q being greater than 2. Greater than 2 is going to put you up here. You're going to be 15 to 25% throughput less because you're spending time missing on cache and stuff. Now 2 is a reasonable number on a workstation environment, but on a compute server where you're busy computing work and taking advantage of secondary cache, every little interruption is bad to you. We learned this in Cray. We turned off character interrupts with telnet daemons. We shut off IP forwarding so that we don't use Crays for network routers. All that noise and chatter. Okay, so this is an example where rules of thumb can be difficult to follow on a big machine because of the sorts of problems of wasting. If I actually back off the load a little bit, I'll get more jobs through the system. I will not be thrashing as much. I won't spend as much time wasting my time loading cache and then getting kicked out, get back in, oh, not there, load cache, but before I can use it, I get kicked out again. Secondary cache thrash. This is the behavior of a cache-based machine, but again, as we got larger vector edges, the same thing's true. The cost of saving off the environment every time I do a context switch. And we used to, in Unicode, do context switches on every interrupt, but then we slowed that down to like 10 milliseconds and stuff so that we don't do as much context switching. Because all that context switching gets expensive, interrupts you from doing your work. So these daemon processes, shut them down if you don't need them. Because they will interfere with CPU-bound work. And my particular case, I run a code that runs in at 288 seconds. But cache thrash can make it run in the 600-second range, almost double the time it takes to do the work due to secondary cache thrash misses. Okay. Of course, with an NFS environment, you have to have the NFS daemons and stuff. In 6.4, they were running as real-time. In 6.5, they've dropped them back to be timeshare so that they don't interfere with batch-critical miser work, because miser work would get kicked out by real-time. So check config services, and that's one of my sanity checks on the compute servers, just to run down the list and say, you don't need this, you don't need this, you don't need web face and web services and this and that. Turn them all off. Don't have those daemons sitting around causing chatter to drive your work out of the CPUs. Monitoring the processes, we got top and GR top. It changed in 6.4 versus 6.5. Okay, the top is like a PS, but it's now giving me a curses type of a window showing me what's the top process on the system. Now I was using top over on do. And with top now I can see my release level. It's a 64-bit binary kernel that I'm running. Name is do. It's a 6.5 release. I can't tell if it's 1M or whatever. I just know it's 6.5. It's an in-house processor 27, which is an origin. And then we've got what are called load averages. And load averages are the number of processes waiting to do work. It's like a run queue length, except it includes the I/O weights as well. Okay, so the load level is counting things that are running, runnable, or doing I/O. And you can have high load levels with no I/O behind it and a normal performance, or you could have low load levels, but all your file system cache buffers being used in high contention. And SAR-U will show you that sort of stuff. In fact, BuffView is still running, still trying to do something. LS-Dyna has been running for 24 hours now since yesterday. So anyways, right now I'm at a 5 because I've got 4 LS-Dynas and 1 BuffView that are actively trying to do work. And BuffView may have a bug in it right now, or something's going on, because it's hung just crunching on 90,000 buffers. Now this load average, the first one is in the first minute, the last minute, the second one is the last 5 minutes, and the third one is the last 10 minutes. Okay. So that's an indication of how much work is on the system. Okay. And then we've got a breakdown of our processes. There are 87 processes on the system. 79 of them are sleeping, and with the PS-L, the wait chant event would show a lot of them on KT wait and various other locks that we're sleeping on. There are 2 zombies right now on the system that are terminating and 6 that are actively running. And we can see 4 of them. The other one is top. Okay. And a 2 CPU system, by the way, top would be on one of your CPUs all the time. I had a customer with the 2 CPU system, and he complained that top was there, and said, well, whenever you're using top, it's locked into that CPU, so you're going to see yourself. As soon as you quit out of top, somebody else gets that CPU. And then we're breaking out our CPUs. There's 60% wasted idle time, nothing happening, 31% for user executing a.out space code, 0.3% for system time. There's very little system time activity on the system right now. And then we've got a wait time, which is all my waits. There are several waits. There's the cache wait, there's direct I/O wait, there's swap wait, and there's also graphics device waits in that metric. So that says we're waiting for some type of I/O. And then X break is the same thing as S break. This means the process is growing in creation. It's asking for memory when it's being first created. And I rarely see that in 6.5, but in 6.4 it would kick up when I create a 2 gig process, for example. But that would indicate a memory pressure situation. And then the last one is interrupt time, and if I had VME interrupts coming in from a external data acquisition device, I may see changes going on there, but it's typically pretty quiet for interrupts. And then lastly on top, I see I've got a 2 gig system, 1.8 available, 1.3 that's free. I've got a 1 gig swap and 1 gig of swap that's free. And then I see PID, parent process group ID, username, the priority they're running at. A plus sign here would indicate real time. I'm not seeing it here. And a G there says it's running as a gang. The gang scheduling says it's multi-threaded and all threads expect to be connected to the CPU at the same time. And gang scheduling is something we've had in Unicos MK in particular, but it's obsolete in Irix. You use Miser instead. With Miser, you're guaranteed those CPUs concurrently. Also, if it says B, there's a real time that just ran. If it says B, that's opportunistic batch. If it's BC, that's batch critical or miser. And then a W is for waitless. Then we see the size of the process. The virtual size in this case is 273. The memory residence size was like 225. We see whether it's running or sleeping, the CPU it's on, how much time it's used, and then the percentage of time it's either waiting for a CPU or using CPU work. So there's a little bit of wait going on in here. And then lastly, the name of the process. And I don't use GR top too often. It's just the same sort of report. It's just a graphic way of seeing the data. Let's see, by the way, if that ever came back. No. I had to restart gross view, and now we can see that the kernel is quite a bit smaller, but there's still quite a bit of free C there. Okay, and if I tried to push that down further, there are systune parameters to control how far I can push it down. So top, PS, GR top, I don't know. Okay, in process execution times, we've already talked about this. In this case, they've got 4 processes that they're going to time slice across the CPU. All this is done on an operating tick basis, which is also known as HZ, Hertz, within the kernel code. Hertz is set to 100, so you get 100 clock ticks per second, which comes out to 10 milliseconds. So every 10 milliseconds, you get a clock interrupt, an involuntary clock interrupt. And the time slice is measured in the units of ticks. What we were talking about here, I guess I spelled it wrong earlier, but slice size, spell out size all the way. And again, it's 2 milliseconds, or 2 for 20 milliseconds on our small workstations and 10 on origins, giving a 100 millisecond time slice before you get interrupted. And Unicos doesn't have that concept. We don't have slice size. Now you do have the ability of manipulating these things if you're root directly. And npry is the command, assuming you're root, that you can actually change the slice size unique to a given CPU, or turn off the clock, things like that. See, what else is it talking about here? It's also just mentioning that we've got these limits. Our limit for the CPU current and max. One of the things you can do is drop those down so that the interactive user can't use too much of the CPU, and then force them to use NQS. But everybody gets hit by the same on these limits. So by the way, anybody know how you get from current to max? When you log in, you come in at the current environment. To up it to the max is the limit command. So the limit command will show you what your current limits are, and then you can do limit, name of the resource, and what you want to up it to. So users always have a current that's low and then a max that allows them, if they know how to ask for it with the limit call, to up those limits. NQS overrides these. If you submit through NQS, you declare your own limits on the job card when you submit it, and then it sets those as what your memory limits and CPU limits are. And there's no job limits. What's commonly requested, this is per process, per user, per process type of environment. So one thing it's saying here is you can change the slice size with the -T, and then there's also some systune parameters that control your limits. And the limit command, by the way, is built into the shell command. There's no man page for it. It's on the shell's man page. So whatever shell you're using, you have to look up the syntax for limit there. Now also influencing our CPU wait time and our CPU scheduling is the process nice value. One thing I have to warn you is that it only has meaning in the timeshare band. If I'm running real time, nice has no meaning there. When I go through my classes, remember we had real time first, then batch critical, then timeshare, then batch, then waitlist. Each one of these has a different scheme. This one is pure priority. This one is pure scheduled or reserved. This one is the one where nice affects you, but it's really what we call the currency account or earnings that determines who gets to run in that time band. And then this is just before idle. And then last. This stuff is going to thrash the worst. This is going to thrash the least. Okay. So nice only has an effect in here. Or if I do a nice 19, for example, I drop down to the wait list. When you come in and log in normally, you're at a nice of 20. Oops. And I can go up if I'm root. So I normally come in at a default of 20, and I can up my nice value. Lowering my nice value increases my CPU priority or influences the way I spend my currency. And I'm going to spend my currency faster and then not get scheduled as quickly. And then normal people come in at 20 and they use the nice command to drop down, reducing their CPU priority. Now, I don't know about you, but I'm never nice. I don't want to give up priority. I want to go the other way. And it doesn't list it here, but there's a command called renice that we don't have in Unicode. And renice will allow me to up it back up. So I could nice down to 38 and then renice back up to 20, something like that. I get a kick out of people that have a performance problem. They try to nice up to 0 and hope that they get better performance, but usually they're not waiting for a CPU. Interactive users are not CPU intensive and they're not CPU starved. When you're getting more than a 1 second delay, it's probably file system buffer cache, because the interactive user is very dependent upon that. And you'll notice that on your workstation. If your cache becomes busy, you'll have a few second pauses as you print that PS file or whatever it is across the network. So I come in at a 20, I can use the nice command and drop myself down to a 39, or I could, if I'm root, go up to a 0. And that only affects the way I am within my own band. It will not affect me and put me above real time, for example. Real time will always run before timeshare. If there's a real time or batch critical there, it will always run. And then the timeshare has to wait for the CPU. And again, JA and the accounting data track how long you wait for CPUs. And another thing that's different from Unicode is that in Unicode we do have changing priorities. We have a fair share scheme that's always changing our CPU priorities to figure out who to schedule next. In Irix, it's a flat priority. You just set it. There's no degrading priority scheme. Now, when fair share and share 2 is implemented, that may change that behavior again. Let's see. Another thing I might point out is that in the NQS environment, they'll often force nices on you. So you submit a job to the low pry queue, and it intentionally nices it down. And in this example, they're just doing they run this demo called button fly, and then they did a nice 10 on button fly, and we see that the second one dropped down to a priority of 10 and a nice of 30. Okay. It looks like they run a single CPU system since the PS command is showing up on CPU 1. Another difference, if you're interested, the ampersand sign in Unicos, it will drop you down 4 automatically. In Irix, you stay at the same nice level. So in Unicos, ampersand forces you down 4. Also in Unicos, the user database can force you down when you log in. So it's not uncommon to drop the interactive user down 4 and then have express NQS queues that are running at a 0, so that you can tier and layer things and have express NQS queues at a higher nice value than the interactive user. But again, nice has no meaning in the other classes. Now, CPU priorities in Irix are completely different than Unicos, and they are what are called POSIX compliant. They completely changed it in 6.4 to be POSIX compliant. And in POSIX standards, 255 is your highest priority and 0 is your lowest priority. In the Cray world, 0 is our highest and 999 was the lowest. And we had that range that FairShare or whatever would be using to shift our processes and to schedule things on. Where are we about? Let me go till quarter 2 and we'll take a break here. They changed it for a whole bunch of reasons. They changed from 6.2 to 6.4 for scalability, POSIX standards, a bunch of different reasons. But in the older scheme, basically 0 to 29 was for system priorities, 30 to 39 was real time, 40 to 127 was timeshare, and 128 to 255 was for batch. And then 0 was best, 255 was the worst. The newer scheme now is 255 is the best, 0 is the worst. And basically the system priorities, instead of having 29 slots, now basically go from 129 to 255. Okay, so they've got more ranges, more openings, more granularity in their priority range. The real times went the full range from 0 to 255. Mountain View is purely focused on real-time environments, and everything shows that when you look at their schedulers and stuff. When you're in real time, there's 2 scheduling techniques. You can do first in, first out. I get the CPU entirely dedicated, first in, first out. Or I can time slice it and round robin it among other real-time processes. Then the timeshare was from 40 to 128. Now it's just 0 to 40. It's much smaller granularity. And lastly, waitlist batch went from 128 to 255 down to 0. There's no priority scheme at all in the batch interface anymore. And that's one of the features that they've added to the feature list for Miser in the future is priority schemes to come back in. So when you're looking at a system, the real time are going to be up in this range, the timeshare are going to be in this range, and batch critical will just show a B or a BC rather than some sort of priority scheme, because there's no priority number there. Has no meaning.
I may have missed it, David.
Go ahead.
Did you comment at all, is 6.5 significantly different from the 6.4?
No. The change occurred in 6.4, but it's going to stay the same in the future. Any other questions? And again, each of those bands have a different scheme. We first of all just go through each band and say, do I have any real time? Do I have any batch critical? Do I have any timeshare? And then within each class, it makes its own decision in terms of if there's more than one in that class, how do I decide who to schedule next? And top and PS. With PS there, I think the next one then shows, well, we're just showing here work being submitted to batch opportunistic. At some point, when you submit to Miser, it's going to tell you your times that you're going to get scheduled. So if I submitted work and it said it's going to start at Q2, I'd be opportunistic, and then right at Q2, I'd go from opportunistic to batch critical. And that's purely based upon when my reservation shows up. It's like going to the restaurant, I'm at the bar, and my reservation time comes up and I get moved to my table. Okay, guaranteed. And at that time, it'll go from a B to a BC. And when you're in BC, real time can still kick you out. But other than that, you're locked down in that CPU and nobody should disturb you. And you shouldn't be hopping around to different threads or anything like this. Now at 6.4, Miser wasn't there, but NASA Ames wrote their own Miser called node masks. And node masks are using the same software stubs that Miser uses. But it was written by NASA Ames and Sterling and that sort of situation. Now the timeshare band basically is time slice driven, 20 milliseconds for single processors, 100 milliseconds for multi-processor systems. And let's take our break. Let's come back at about at 10 o'clock. And I've already pointed out that scheduling is done in these different classes. The schedule is going to sort through each class first. If it doesn't find something in the class, it's going to go on to the next class. But if it stays in that class and finds something runnable, then it's got to decide how to schedule it. And again, a lot of the scheduling information is available with par-r. Par-r will tell you what's going on with all these context switching and describe those events. I'm going to get into Miser a little bit, but the first page on 561 is about the timeshare band. And timeshare is where we all presently run when we're running things interactively. It's also where NQS and LSF run their work. So in a mixed environment with batch and interactive, you're all competing in the same band, same class. And this class, again, the timeshare class is driven by time slices, 20 milliseconds or 100 milliseconds. But then the order of process execution within the timeshare class is based upon something called a currency or earnings model, rather than a priority based. Now this currency or earnings model is not like fair share in that it's only keeping the data around for milliseconds. Whereas in fair share, I may keep my usage around for days. Keep it in what's called an L node. But I've also referred to this thing more as an equal share scheduler. What it's trying to do is distribute CPU resources equally among families of processes or process groups. Standard Unix distributes by process. More processes, more work. If I fire off 100 programs and you fire off one, I'll get 100 times more CPU time than you will. Standard Unix timeshare is by process. More processes you have, the more CPU time you get. So in Unicode, we implemented fair share, which was written down in Australia, put that into Unicode to try to undo that and distribute more fairly. And of course, being fair to somebody is going to be unfair to somebody else. You always got trade-offs that you're making. So this is kind of a similar model. It's tracking your usage in very, very short incremental steps, and then using that to decide who gets the CPU next. And earnings are accumulated based upon the process ID or thread ID. In other words, the earnings are accumulated by if it's a gang or a group of processes that's a thread group, that'll act as one workload unit. The intent here is that software engineering did not want multi-threaded gang applications to gang up on the interactive users. So you get penalized. The more threads you fire off, more processes you fire off, the more you get penalized. And there's no way to unskew that and say this person has more shares and this person has less shares. It's trying to do just equal distribution among these process groups. So multi-threaded applications will have their barrier problems fail in the timeshare band first, because it's designed to beat up on gangs and cause them to collapse so that the interactive users have response. And Mountain View wants all multi-threaded applications to be run either real-time or Miser. Okay, with real-time you're locked down and scheduled differently, and in Miser it's all reservation-based. So basically all processes are assumed to have equal share of the system. That's kind of a Unix thing. More processes, that you own, the more timeshares you get. So this earnings model is designed to undo that by thread ID. Let's see, have no effect on the scheduling of another process, even for those processes owned by the same user or belonging to the same job. What it's going to try to do is beat up on the gangs. And again, it's going to use in this model, using the CPU resource depletes your earnings. And the better your nice value, the quicker you're going to deplete your earnings. And then you're not going to get scheduled as quickly because you've spent all your money. They're going to give the CPU to the one that has the more money. The nice value affects the rate at which you accumulate these earnings. Better nice values, you accumulate your earnings faster. And then earnings are used to consider, are what we consider in scheduling decisions, only when there's contention for the CPU resource. That last bullet I don't think is true. It was documented that way originally, but this summer I found out something that I didn't realize this bullet was here still. But I would mark that with a big question mark. What we're talking about here is the scenario that happened in Fair Share. And keep in mind, the Mountain View developers were aware of Fair Share, they were aware of LSF and batch systems, and they were trying to do everything in one product. And the problem with Fair Share is if I take the machine at midnight to 8 in the morning and nobody else is there, nobody else is asking for the machine, I still overshot my resources. And then at 8 in the morning, somebody else logs in, I've overshot my share even though nobody else was asking for the machine. I was dumb enough to stay up and take advantage of that time, but I got penalized for it. So what they're saying here is if there's no contention, why should I get penalized or marooned? On Unicos, if I ran from midnight to 8 in the morning, everyone comes in at 8, I actually get marooned and put into what's called the penalty box in Unicos. And you won't run when you're in the penalty box because I overshot my share. Okay. So you get stuck, you get marooned. And the problem is the user complaining that nobody else asked for the machine, why should I have been penalized for taking advantage of an idle machine? So what they really want to do is count when there's contention, not when you're running. And that's what that bullet's trying to describe, to resolve that marooning problem. But I don't think it's true. Talking to the developer, he disagreed with that line too. It was documentation 2 years ago describing something that never worked. You'll also see documentation describing it as distributing this by user ID, not thread ID. And that's not true either. If I fire off 200 jobs and you fire off one, I will still get more CPU time, and you'll be competing with my 100 jobs for the CPUs. With Fair Share, I would be competing with myself. My CPU wait times would go up, but the other person's wouldn't because they're in a different user account. Okay. There is Fair Share within Irix, but it's not supported or working yet, though I heard a customer just sold a system to a site in Amsterdam from an employee last week. So they're going to install Share 2 on it and everything, but that takes 652M, and nobody's really tested the Share product yet. Okay, so I wish him luck, shall we say, because this code is constantly changing. Now, Fair Share was supported in 6.2 and earlier releases, but when they rewrote the CPU scheduler in 6.4, they ripped out all the stubs. They rewrote the software, so all the code that had to do with Fair Share was taken out. They added it back in 6.52M. Okay. So I do expect customers to still be looking for the Fair Share product to solve some of their traditional Cray problems. But they've got to understand the effect that has on cache behaviors now, and that this isn't a vector machine, it's a cache machine, and you're going to have a lot of cache thrashing effects. And the way cache thrashing shows up is in the bill, because the user that's paying will have variable timings on their runs and get charged different prices for the same amount of work. So I run it once, it costs me $1,000. I run it again, it costs me $2,000. I run it again, it costs me $3,000. Customer's not going to be happy. Okay. And again, it'll cost you a 7 to 10% increase when you're at the number of CPUs. Worst case scenario, I've seen a 25% increase in service times. Okay, but this is CPU bound work. If I'm IO bound, if I don't do no CPU work, I don't dirty cache, and it's not a big deal. NFS daemons and stuff like that don't dirty cache and do lots of work within their cache. It's the nature of how much CPU intensive work I have. Okay. If I'm asleep all the time, it doesn't matter. But if I'm trying to lock something down so I can compute, it does matter.
Really not that far, but charging.
But they want repeatable timings.
Supply and demand, huh?
Yeah, but they want repeatable billings. They want predictable charges. And we got beat up in T3E in this area too, to be able to get repeatable timings off the T3E product for our customers. So you'll be hearing about that if you get involved in this area. And charging is how I recoup costs to pay for the next upgrade, right? So we want them to be able to justify the upgrade, substantiate use, demonstrate to their pocket purse person that we're using it productively. And this is the amount of work that we're getting done. And that our car crashes are now half a day rather than 3 days. And I can crash more cars in that given time interval. These sorts of things. That's the ultimate performance model, how much work I can get done. But if I oversubscribe the system, I'll spend all my time not getting work done, but just thrashing. So anyways, the earnings consolidated when there's only contention is not accurate as far as I know. It was discussed and documented, but talking to the developer this summer, I don't think he would agree with that line either. And right now, all these multi-threaded gangs are running in the timeshare band, and the gangs are failing because they can't get CPUs concurrently, and then their barrier synchronization timings go up. And NCSA, National Center for Supercomputer Applications, down in Illinois, was complaining about 1,000% variance. I run it once, it takes me an hour. I run it again, it takes me 1,000 hours. And that's a big variance, but all of that was due to barrier synchronization problems, not due to cache thrashing. Okay, the number one problem out there is barrier collapsing, then it's cache thrashing. And NUMA is nothing out there in the real world compared to these other problems. They're the ones that are costing work. And a data center manager will look at utilization and say, oh, I've got high utilization. But if they actually looked at the hardware counters, they'd see I'm spending all my time missing cache, and it's non-productive. I'm curious to see what kind of hardware counters we're going to get on Pentium product line and the Merced chip and stuff like that. So timeshare is just showing here the same banding that we talked about, and how the PS, they're doing a nice and tiering things, going -5, 10, 15, 19, and just showing what happened to the nice values, okay, with the PS command. So the nice values directly translate to the process priorities in that band. Basically, your priority is your nice value. And then based upon your nice value, it's the earnings, this currency account that's going to be used to decide who gets the CPU next. And again, there is a counter keeping track of how long you wait on the CPU. CPU wait time is available within extended accounting data. Now, real-time processes are scheduled differently. Irix is really a real-time environment. All the emphasis really has been put into virtual reality and real-time data acquisition types of situations. And keep in mind, there's a lot of indies out there that simply have, some sort of data acquisition device that's anything from reading the temperature of the room to tracking where the hockey puck is through a telemetry device, something like that. When you get into real-time, there is a separate product referred to React. And React is also referred to as the frame scheduler. And when you get into virtual reality in real time, you're really down to event by event, millisecond by millisecond events. What's happening to cause that stutter? I got to pause there. I'm driving down the road and all of a sudden there's a jitter in the road simulation that I've got, something like that. So in this market, and I do know of sites that are combining traditional Cray batch applications and real-time on the same platform. Some of the black hole sites are doing that sort of thing, where the real-time are doing some sort of data acquisition, but then they've got batch interface on the same machine. But you have to be real careful about this to isolate the two from each other so that they don't interfere with each other. You don't want the batch work to interfere with real-time. You don't want the real-time to interfere with batch. But you want them to share the same file system and share the same OS so they can communicate more quickly to each other. So React is a separate product. It's a licensed product. It's also referred to as FRS, or the frame scheduler. And there's a whole bunch of system calls to use it. Now, the benchmarkers can actually use React in a benchmark situation for batch. There's something called the superglue. And you can write your program and call superglue at the beginning and then end superglue at the end, and it will make real-time React calls and lock your application down and run it like it's real-time. And if, for example, I had 128 CPU origin at Jet Propulsion's lab and I'm reading telemetry data or visual data coming from a Mars lander or something like that, I may want to do those sorts of things and dedicate this machine to processing the data that's coming down from my space device. Okay. So in the React area, you want to accurately time events. You're going to use signals to interrupt routines. You're going to control allocation of physical memory to a process. And then you're going to provide priority scheduling to the processes. And these are things that React provides for you. Normally, traditional Cray sites do not have React on their system. So for the real-time environment, they want at least 2 CPUs so that you can dedicate one to high priority work. Applications can avoid page faulting by locking stuff into memory, pinning it down into memory. And this is common in the graphics devices too, the frame buffers. When I'm pushing data out to a graphics device, I'm going to lock stuff into memory and have my own device driver and start consuming memory for real-time processes, things like that. Real-time are always scheduled ahead of timeshare. They're using the entire priority band from 0 to 255. And if you hit 2 that are in the same priority number, then you're going to go with the one that's been waiting the longest. Real-time priorities can even exceed system priorities, but you want to be careful about what you're doing there. You don't want to put something higher than BD flush or VHAND, for example, unless you really know what you're doing on your system and you've got some other, maybe it's a memory pin program that has to run periodically, some sort of interrupt handler for a peripheral device that you might put higher. But in general, in compute markets, we don't. It's only in the real-time market. Priority 255 should never be used. It's used for system use. Priority 0 still executes ahead of all timeshare. So even if you put it at real-time priority 0, it will still run before a priority 20 in the timeshare band. And the real-time, I can schedule first in or first out or round robin. First in, first out is kind of like the T3D did. I get those CPUs that partition until I'm done. Whereas round robin is more like Unicos does, where it tries to time slice things. Now processes can be locked onto a CPU. You can lock them down. If you're single-threaded, run on. You can say run on this CPU. And if I've got a single-threaded application with no children, I will be able to lock it down and prevent the CPU scheduler from interfering with me. And I will get repeatable timings. I will not get cache misses due to the scheduler. But run-on will not work if I fork off children or if I have multi-threaded programs where I'm using all the CPUs. In the Sun world that SGI picked up, there was a thing called P-sets, processor sets. It was a way of partitioning out your CPUs in a multiple CPU system. Basically, P-set was there in 6.2 and replaced with Miser CPU set in 6.5. And node mask is what they used in 6.4 out at NASA Ames, and a few other customers picked up that code to lock down a group of processes into your topology so it cannot be interfered with. Okay. And as I was saying before lunch, even network IP forwarding traffic and stuff like that can be chatter to drive your work out of the CPUs, causing you to miss cache and spend all your time loading cache rather than computing the data that's in cache. Let's see. So they can be restricted to execute only those processes assigned to it, and you can do this by group, by the way. With Miser CPU set, you can set up an Army partition, a Navy partition, or a Marine partition, and based upon the perms on the configuration file, determines who can submit to that partition. Real-time processes designation requires privilege. You have to be root to be able to use npride to do these things. And the designation guarantees the highest possible priority until the process willingly gives up the CPU or blocks on a resource, meaning it went to sleep on some lock in the kernel. And the default allocation policy places real times on a CPU round robin per node to minimize interference. So every real-time process that starts up skips a CPU, so we go 1, 3, 5, 7. The whole purpose is we don't want to put 2 real times on the same node because then they would be competing with each other. However, multi-threaded applications put 2 per node. So all those NFS daemons that are running real time are going 1 per node. Meanwhile, my real computational work is putting 2 threads per node. And eventually, if I had 8 real-time daemons, I've got 1 per node, and the first job I run is actually going to be banging with the real-time process on that node. So I end up putting 2 threads on the node plus 1 real-time, and then the real-time drives out something. So those NFS daemons can really hurt you if you're not using NFS, don't have that stuff on. Of course, in the real world, we are, so we have to live with it. And that's why on a 128 CPU system, I'd count out all the real-time daemons with PS-EF and make sure that I've got nodes basically for them. On a Cray market, we typically try to keep CPU utilization at 100% all the time. In the Irix market or the Origin cache-based markets, you don't want to do that because you're going to be thrashing on the system. You're going to be inefficient, wasting time. And the larger the caches, memory's not getting any faster. The boards that are out there now are 8 megabyte caches. I dirty up 8 meg is going to be twice the overhead of the 4 meg, 8 times the overhead of the 1 meg. And a lot of these customers are sitting here on caches that are smaller than 1 meg because they're still on challenges and stuff. So they don't really realize the impact of system cache thrashing yet until they get on the bigger caches and oversubscribe the CPUs. So it's 1 real-time per node, but it's 2 threads per node for multi-threaded applications. And that we didn't get to the man page, but again, a lot of this stuff, a really important performance man page for the for the users is that P_environ, which documents all these threading environment variables and a few other programming environment variables. Now it's NPRI that allows me to control this. As root, I can manipulate the priority schemes and I can make a process real time. And by the way, a recent case study, NCAR, when you log into the NCAR origin, they are doing miser CPU set for interactive users. So when you log in, you're basically locked down into part of the partition. Locked down into the topology, so interactive users are only allowed to use certain CPU numbers. And then the NQS stuff and miser are on other CPU numbers. So when you boot up some of these system daemons now, they're using miser CPU set to lock that thing down into a set of CPUs. So NPRI, for example, during the boot process, I may have NPRI kicking things up, running as root to be able to change priorities or policies, things like that. So this is just trying to show NPRI-S is setting the policy. And with the policy, I've got first in, first out, or round robin. And first in, first out, I'm basically locking down until I voluntarily yield the CPU through a system call. And again, SGI NAP, the whole purpose of SGI NAP was to yield. That's its purpose in life. And on Unicos, that was called resched. Yield my CPU. Give it to somebody that can use it. And then we also have round robin scheduling, basically a time slice system where I get my slice size and then I get kicked out and then another real-time daemon can lock down into that CPU for slice size length as well. Now if you're in timeshare, you actually have to kick it to real-time before you can specify whether it's going to be first in, first out. So it didn't mention it here, but there's a TS option. So I can put it into timeshare policy, or I can put it into real time with either a first in, first out, or a round robin scheduling scheme. Now there also is a chart here showing in systune there are parameters to specify what my priorities are going to be. And this is just listing real time versus system threads. And the system thread priorities are typically like 255 is for the console. But where was BD Flush? BD Flush was at 92 down here. VHAND, we were talking about VHAND the other day. VHAND right here is at 98. Okay. And a lot of these things used to be system daemons with PS, but now they're kernel threads in 6.5. But you still can set the priorities. Now even though they've got a wider priority range now, they tried to put them at the same priority such that I've got a whole bunch of daemons here that are all at 98. And that was simply so they don't change the behavior to be compatible with older Irixes where they were at the same priority. But I could see some sites starting to separate them and tiering them a little bit more because I've got a whole, 100 to 109 is being used by some pretty critical stuff. So I've got 92, 94, 96, 98, and 100 as a tiered range for my different priorities.
Okay.
Yeah.
You know what those MSC threads are being used for? I can see what they're being used for, but do you know what in the kernel is actually monitoring that?
They're separate threads. I don't know the actual piece of code that they're actually running at that time. Okay, but they're kernel threads.
I've seen system error, system warning messages coming particularly out of the heartbeat.
Yeah, I don't know anything about that. Can't help right now. Syslog is critical. I've got some things that show up in my Syslog, like real-time monitor daemon and stuff, that I got to dig into as well. But what I primarily do is go into the source code. How many people have looked at source codes before or used source codes? Because in our data center, we've got cscope to basically browse the code. It's built a database of all the defines ahead of time. So it goes to the database to find this variable name. So I'd go off and with cscope look for MSC_shutdown or MSC_heartbeat and see what that code does. And since we're on the topic, thank you. The seat's too high. Within the Cray Park domain, everything is cross-mounted. And I've got an alias set up to mine. If you go into the kernel internals class, they get into this in great detail. But I've got an alias here that allows me to run cscope, or I can go straight to the Irix source tree and look at things there. Let me do a... Now when cscope comes up, you need to have this blank line at the bottom or the window isn't sized right. That's why I did an eval resize ahead of time. So I'm now into a source browsing tool called cscope. And you can email me if you want to know the source for this or anything like that, or the Irix kernel internals class gets into it. And we were talking about MSC_heartbeat. Was that the one?
Yeah, spell it right.
How was it spelled?
Heat beat instead of
Oh.
heartbeat. Still got it. You said heat on your mind.
Yeah, with the weather outside, it's no wonder. And now I'm straight at the routine. Okay, and it's got some of the messages that it's writing out. It's doing a system controller keep alive call, and I'd have to dig down into that. Okay, so that's the ultimate documentation. It's like only going to Boolean and wiretabs if you still use those. I don't know. I haven't used those things in 15 years either.
This must be when, like, if you're going to have an impending emergency shutdown, it's going to keep it powered up for a short period of time.
But I'd have to dig into the code to see what it's doing, is all I'm saying. Nobody knows everything. That's why you sometimes have to dig into code to find it. And cscope, it looks at the whole tree, so it's able to look at the entire source tree, rather than you trying to do finds and greps and stuff like that. It's done all that for you and built a database for you to browse the code more easily. So in my case, I was getting it from ~mix. I was getting it through the kernel internals group. ~mix/Irix/tools/CS65 for the 6.5 source tree. The hard part as a support person, though, is being able to make sure that that code is matching what I actually have running on my system with patch sets and all that sort of stuff. I'm constantly looking at code, but it's never it never is the same set of code. I'm constantly seeing changes in it, and I can't be sure that it matches my source. And that's the thing that we miss in the Cray world, is the old days of having pure source systems, and I knew exactly what was on my system because it was built on that system. Once we went to binary releases, then we had the problem of being sure that the source and what's running on the system were the same. Okay. So that's how I'd have to look up each one of those things, is try to do a pattern search on them. Now what we're getting into a little bit is interactive versus batch. In the batch environment, I like this, they call it a host supercomputer. The politically correct term used to be mainframes. Now I prefer to call them compute servers. Okay, and in our case, Crays were always basically a number cruncher out there. The problem is nowadays people are selling computers as general purpose computers, when in fact a lot of computers nowadays are targeted for a certain type of use. You know, and that's why I said yesterday, when somebody asked me what computer to buy, first thing I ask them is, what do you want to do with it? Because that's going to depend upon the application sets and all the price range and all the sorts of things that they have to decide about. So interactive jobs are processes that are resources consistently available, the interactive environment, more unpredictable than batch jobs. With the batch environment, you may have multiple users submitting simultaneously. The resource requirements may exceed the capacity of the system. You put a system out there on the network, and it's easy to oversubscribe the thing if everybody can get onto it. And that's why, for example, database servers and web servers, you cannot log into the machine because they don't want to lose control of the load subscription levels on that machine. If everybody logged into it, pretty soon memory would be full with shells and everything else that they're doing. So batch systems will carry with it some sort of user specification saying how much CPU time and memory do I need ahead of time. And in the batch environment, there's typically large amounts of CPU time and memory, and oftentimes, like with Nastran, I/O behind it as well. And the users want deterministic guarantees about their execution time. For example, at the European Center for Medium Scale Weather Forecasting, they want that weather model done by 8 a.m. the next morning, period. You know, if it's late, they can't go on the news and give the weather. And on the T3E, they spent a lot of time getting deterministic timings on their weather models. Clive England was pretty heavily involved in trying to get that predictable return. And with batch jobs, we're typically trying to get batch turnarounds, but we're trying to throttle back the workload so we don't thrash. And that's why NQS was written to prevent Cray2s from oversubscribing memory and swapping all the time. And Crays, when they start swapping, they go idle. Okay. With cache-based machines, the problem is when I oversubscribe CPUs, I start thrashing on secondary cache. Two different machine concepts. So Mountain View was taking this information and basically created the concept of what's called miser and soft partitioning of our systems. And this is softer than a T3D. It's kind of like PE pools and T3E Unicos MK. I can dynamically configure them on the fly. It's one OS, one single system image, one file system. Now at some point I may decide to make parts and split them into separate systems. There is a point where you simply have too much work on one system. I would not want a database engine and a video server and everything all running on one platform. When I was at NASA Goddard, there's a program called Solve. It did 3/4 of the I/O on the system in a month. And when they ran more than 2 copies of it, you had 20-minute waits on a man page. This was on a J90. Okay, that was a case where they had to offload. At some point, the diversity of your workload requires you to offload things onto separate OSs. So you've got two choices. You could have a 128 CPU system, or you could have 264s or 432s. You've got to decide the best way to use that resource. And you might be better off having 264s with database on one and computational on the other. You're isolating the two workloads from interfering with the other workload. So this is static runtime type of partitioning with miser type of work, where I can take some of my CPUs and making them interactive, and some of them I can make batch. And I can also carve out my memory and say batch is going to be reserved a certain amount of memory guaranteed. And by the way, if batch isn't using it, interactive can take advantage of it. But if batch is using it, interactive cannot use it. So it's a soft partition, really. So CPUs and memory are assigned or partitioned to service either interactive or batch jobs, but not both. And at NCAR, they've got CPU sets for the interactive logins, and then they've got miser interfaces for the NQS type of work. And they're both targeted to different types or different CPU numbers within their architecture. With this partitioning, we're going to guarantee CPU and memory availability. We hopefully will have deterministic deadlines for batch jobs, and hopefully still have good interactive response. The problem is that idle resources are wasted because the resources are not shareable. The problem here, though, is that instead I end up showing CPU utilization that's actually cache thrash. And that doesn't look like wasted time. You don't see that unless you're actually looking at hardware counters. So to the end user, utilization goes up. They think they're getting more work done, when in fact it hasn't. It's gone down because they're spending more time loading cache than computing on it. So it's debatable. Do you want to waste your time as idle, or do you want to waste it as cache thrash? Well, in cache thrash, the user pays for it, and they may not want to do that. So you may want to configure it so that you get repeatable timings. And that's what miser is for. So I'm just saying it's debatable. Yeah, idle time is wasted, but so is CPU service time if all you're doing is loading cache because you got interrupted. And it's easier to track idle than it is to track secondary cache thrash. So this is what miser is for. Miser is a batch process. It does a scheduling algorithm. Miser is like the reservation person. You call it Red Lobster. And Red Lobster looks in the book and says, we got a table here, and you can have the table from 7 o'clock to 8 o'clock, something like that. It's a reservation-based system. So miser is going to negotiate the reservation, and it's got a vector map basically in it. It's got an array that is chunking up and breaking up my time intervals into chunks. And the chunks are called quantas. So you get a 20-second quanta or 20-second chunk. If you go to a restaurant, they've got a reservation book with a grid on it. The grid may be a 15-minute chunk. So I can reserve in 15-minute granularities for people. Okay, that would be my quanta. On Irix, it's a 20-second quanta. So I can reserve things in 20-second chunks. And miser is typically designed for things that are less than a week. Typically, it'd be for the things that you run overnight, 12-hour type of runs or something of that sort. It was not designed for the sites that have jobs that run forever. Okay. So you submit to miser. Miser looks up in this reservation book, finds the number of quanta that it needs, looks up the time that it represents, and then spits back to you. Here's your reservation time. You get so much memory, so many CPUs from 11:30 to 12 o'clock, something like that. So it consists of a user process called the miser daemon. There's also kernel support to deliver the resources. Within the kernel, that code was there in 6.4 and was being used by NodeMask. And in 6.5, it's miser that's using that code. And the system call is sysmp. SYSMP is the system call that miser is using to do the interfaces. And there's a whole bunch of other things that sysmp does, like get SAR data, stuff like that. Well, this allows flexibility while improving responsiveness and performance. It's not a hard partition. If I don't have batch work, then the interactive users can use it. However, if a person like me is smart enough to know that miser is configured on the system, I can use it and take advantage of it and everyone else gets hurt. Because when I submit to miser, if the door is open, if the schedule is empty, I can reserve memory and never have pages stolen from me, and I can take CPUs away from people and nobody would interrupt me. So the user that knows how to use miser can take advantage of it and lock down into a CPU and nobody disturbs it. And this basically, they're saying, allows idle CPU memory resources to be used, and my point is that it's going to be used for cache thrashing. And it's going to cause service times to go up. The user's going to pay for it. It's going to cause variance in these service times. So do you want idle or do you want that? That depends upon what your users are saying. And by the way, opportunistic miser is like, I've always said, it's like getting to the bar before the table's available. You know, and you get there, restaurant says your table's from 7 to 7:30, you get there at 6:45, and by the time your table's ready, you're drunk or run out of money, and you don't need to go to the table anymore, right? You've spent all your resources. And you didn't get anything done, you were thrashing on secondary cache, so you didn't actually get the vitamins and the nutrients you needed from the real meal. Now this is a predictive scheduler. It's using the information supplied by the user to reserve the resources. Everything about a batch interface says that you got to have pre-knowledge of what you need. Okay. If I try to move a trailer home and go down the road right now, there's going to be a little bit of problem because I'm going to take up more space on the road than there is road. I've got to schedule that thing and make sure I run it at night or make sure that I got trucks in front of me and behind me to clear the road before I go down the road. So you got to have pre-knowledge of what you need to do. And this has always been true in Cray with COS and Unicos. The more you know about what you need, the more you can properly declare it, and then you can get it scheduled. It's a reactive scheduler in the kernel. It's going to make idle resources available to any process that needs to use them. But it may give you the CPU, you load your cache, and then it comes along and says, oh, the other guy is ready now, you don't get your table. And you get kicked out. So you end up thrashing more. The stuff in waitlist and opportunistic are going to thrash more. The stuff in batch critical will not thrash as much. It can still thrash from real time though. Real time can still drive it out. With no static scheduling, jobs can be scheduled on CPUs that other batch schedulers would have to leave idle. So rather than letting them go idle, we're trying to let somebody else take advantage of them. Now, unfortunately, like any new software, it has its trade-offs. One of the problems is, for example, with Miser, I submit a job and ask for 10 hours. Then the job gets killed. The reservation remains in the Miser book. It is not released. Miser can't schedule anything else. It doesn't know that the job died and that it can reschedule and reuse that time. This is called job repacking. Miser has a whole feature list of things that have to be done to satisfy the traditional batch market. And one of those things is job repacking. So I can load up my system, fire off 100 jobs, fill up the reservation book, and then cancel all the reservations, kill them all off. And Miser won't know that it can free up the book, and it doesn't have an eraser to clear up the schedule. It can't repack it. So what we're seeing here is an example where I'm running pure batch critical, and I've got two processes that are running, A and B. I'm going to submit the process with a command called Miser submit. And when I submit Miser submit, I'm going to ask for so much CPU time and so much memory. And then Miser is going to spit back the message saying, here's your reservation. And by the way, in the future, Miser is going to have GUIs that pop up just like a reservation book. So that you see this reservation grid and stuff like that with memory and stuff like that. So yeah, I submit with Miser submit. The Miser command then looks at my resources and figures out a non-conflicting schedule of jobs where I've specified how much CPU time and memory I've got. It goes to the reservation book, this array, this index grid, and finds a spot that says you got CPU, memory, and number of CPUs. It's CPU time, number of CPUs, and how much memory do you need. And then it reserves it in that book. During a job schedule period, it has priority over all other allocated resources, and it's prevented from exceeding the resources. This is something about bottlenecks in Miser. Our older bottlenecks used to look like this because we were small hardware. Now we've been throwing a lot of hardware at the problems, and our bottlenecks have gone out like this. And by the way, every system has a bottleneck at infinity. Infinity is when jobs get killed because there's no process table entries left or no memory left or something like that. Okay. So what's going to happen here now with this bottleneck curve is instead of right now we were talking about the real-time daemons can drive some of the work out of the CPUs before we actually hit the number of CPUs, such that I've got things that get beat up because of system daemons. What Miser is going to do is lock things down, but you cannot oversubscribe it. So with Miser, I'm actually breaking it into a separate workload class, and Miser is going to be flat down like this, but it cannot go beyond the number of CPUs on the system. In fact, you need some CPUs left over. So the bottleneck looks like that. And that's more and more what our bottlenecks are looking like these days. They used to be a general slope, then they're a hump, and nowadays they're straight out, and then when you hit the wall, you're dead. There's nothing more you can do. So with Miser, I cannot run more CPUs than are carved out of Miser. If I've got a 16 CPU system and I say Miser gets 8, I will get killed if I ask for more than 8. Okay. Same thing with memory. If I ask for 100 megabyte of memory, I will get killed if I go beyond that. And NQE does the same sort of thing. If I exceed my limits, I get killed. Now in the future, Miser, instead of killing you, will do things like checkpoint or swap, put you into the timeshare band or the waitlist band. There will be other options to do other than a kill. But that's what's happening now. Now the other class, by the way, is now going to start thrashing earlier because Miser just took away some of my resources. So one class gets better and the other class gets worse. And now the stuff that was thrashing here is now thrashing down in here. Because I've stolen some of the resources and that other class got hurt when I favored this particular class that was the Miser work. Okay. So I cannot have more things in Miser than I have CPUs. In fact, more than I have actually carved out for Miser. You never set up Miser to have the same number as you have on the system. Okay, if I have a 16 CPU system, I'm going to leave at least 2 available for other things other than Miser. course, if there's nothing submitted to Miser, it doesn't make any difference. So when I submit to Miser, I have to stay within the allocated limits, and I cannot exceed it or I will get killed right now. There are no other exception policies. And allocated resources the user does not use are available to other processes. If I don't take all the memory, if I overestimate, the interactive people can still take that memory space. It still can get used. And then prior to the job's scheduled time period, it may idle some system resources, but does not compete for them. And then when my scheduled period starts, I'm locked in. When it ends, it's terminated if it's not already done. You have to have pre-knowledge of how much work it takes. And again, in future releases, other exception policies other than a kill will be implemented, such as putting into waitlist, putting it into timeshare, checkpointing it, things of that sort. Now I'm going to go off here on do. Where's a good window here? And I've already got Miser configured. PS-EF and I grep for Miser. And there's the Miser daemon running. Okay. And in fact, it's asking for 14 CPUs and 1.5 megabyte or 1.5 gig of memory. Now remember that you have to have enough swap space to back that up. I only have 1 gig of swap on this system. So Miser is not actually going to allow me to schedule 1.5 gig. It will only allow me to schedule 1 gig because it dropped it down. And I'm going to just go in and submit some workload. Miser, let me look at the file first. I've got a file that specifies I need 300 seconds of CPU time, I want 1 CPU, and I want 100 meg of memory. So I've declared what my resources are going to be. Now I do a Miser underscore submit dash, oh, I need to know the name of the queue. A Miser capital Q will tell you the name of the queue. It's called mine. So I'm going to do a Miser underscore submit dash Q mine dash F miser.conf, the configuration file I just had. And then I've got a program in this directory called code2. So I'm going to fire that off. And Miser now has spit back 10:56:30. Let's see what the time is right now. Oops, it went straight critical. Miser spit back what my reservation time was. So I see my batch ID is my parent process ID. It's the same thing. Okay, they call it a batch ID. It's also the parent process ID. And then I see here's my time. By the way, the exception policy is a kill. I've asked for 5 minutes, and then here's my completion. I'm reserved from 10:56:30 to 11:01:30. And I've asked for 1 CPU and 100 meg of memory. So that's my reservation time. Before that reservation time occurs, I'm basically going to be opportunistic. But after it happens, I will be batch critical. And if I do a top right now, I can see that code 2 is batch critical. It went straight to the critical mode because there was no reservations, and my reservation time came right up real quickly on me. Now, let's fire up the load a little bit. And now I start seeing reservation times that are like 11:03 to 11:08. So I just fired off a whole bunch more copies of this code too. And rather than oversubscribe the system, it's delaying out the time that it's going to run, 10:58, 11:03, okay? And if I do a PS-C, I see some that are batch and some that are batch critical. And that's all based upon the time. So I'm at 11:58. At 11:03 is when these are going to actually go batch critical. And there is a Miser underscore J info, and let me take this one, take that PID, and it tells me that my reservation time, that thing is going to go from batch to batch critical at 11:01:30. Okay, so we'll wait and see what happens with that thing. I've still got 2-3 minutes before that time event comes up. So PS-C, and I'm at let's see, dash P 430753 : date. Oops. I need a non-numeric article. Oh, I put a colon in there. Okay. So I'm just going to run this and wait for my timestamp to come up to 11:01, and it will go from batch to batch critical. Okay. And it was at 11:01 that it was going to do it. 11:01:30. So I'm just watching it here. We'll waste a minute here. Got about 30 seconds. Now, they don't have any real GUIs for this, but there are design mock-ups and stuff like that for how I can look at the reservation other than through an ASCII interface. And the program's getting its answer done right now. It's just finishing up, or at least one of them is finishing up. I'm still batch. I'm about 20 seconds away right now. Oh, I said 11:01. I'm still a minute away.